All right. So the idea for this class is to take a look at some gravitation problems from the gravitation chapter. Um, and tomorrow we're gonna have a review. So I have some problems prepared for tomorrow, and then you'll have the discussion session with Kate going over some more problems. But at this point, I trust that you've reviewed and studied for the final, of course. But yeah, so tomorrow the idea is to go through some problems that could be useful to refresh some concepts for the final. All right. So let me share here the screen. And stop here video. All right. So for gravitation, let me see, the only problem that we went through was the first one, right? So let's do 2, 3, and 4. Before we start, any questions about anything? I uploaded the formula sheet last night, and yeah, that's the only news for now. All right. Okay, so set 7 problem 2 says the mass of Venus is 81.5% that of the Earth, and its radius is 94.9 that of the Earth, right? So compute the acceleration due to gravity on the surface of Venus from these data. And then B, if a rock weighed 75 newtons on Earth, what would it weigh at the surface of Venus? All right, so let's just write that down. That's the mass of Venus. It is 81.5% mass of the Earth. And the radius is 94.9% the radius of the Earth. We want to know the gravity Venus and what would this thing weigh on the surface? So weight in Venus with the weight of Earth equals 75 newtons. Right? So what we can do here is simply use the expression that we had for the acceleration. So remember that the gravitational interaction was the product between g, the mass of one object, the mass of the other object, divided by the distance to the second power. So we could get the expression of the acceleration, in this case of the Earth, the gravitational acceleration was g, the mass, oh yeah, use small, the mass of the Earth divided by the radius of the Earth squared. And that we know that that's 9.8 meters per second squared, right? So we can put this in terms of numbers, not just percentages. So this is 0.815 mass of the Earth, RV is 0.949, the radius of the Earth, right? And the weight of this rock on Earth is equal to mg Earth, so that's 75 newtons. Basically, what we need to do here is to get the acceleration of the gravitation in Venus, and then get the mass of that rock and be able to calculate the weight in Venus with the acceleration of the gravity in Venus. So we can do gravity of Venus, that's G, mass of Venus, R Venus square, and that's G 0.815 mass of the Earth divided by 0.949, the radius of the Earth squared. That's 0.905 G mass of the Earth divided by the radius of the Earth squared. Right? So don't confuse this with a 6. This is G. Right? The gravitational constant. And that's giving 905 G E, right? The acceleration of of gravity for the Earth. So this is basically what we have here, right? So that's G. Oops. Right? And we have the gravity of Venus in terms of the gravity of the Earth. So that's perfectly you can calculate that. And then you have the weight of the rock in Venus would be G in Venus, and we know the acceleration of the gravity in Venus, which is 0.905, the acceleration of gravity of the Earth. So you can just substitute that 0.905 mg E, and that's 0.90575 newtons. That's 67.9 newtons. All right. As you can see, it's not necessary to calculate the mass of the rock, right? Because it's just you're just getting a relationship with the gravity of the Earth, between gravity of the Earth and Venus, and the gravity in Venus. All right. Let me highlight those. So this is one, and this is the other result. All right. Any questions about this one? No? All right. Cool. So let's take a look at the next one, which is number 3. Let me find out the number. All right. So for number 3, it says a planet orbiting a distant star has radius 3.24 times 10 to the 6th meters. The escape speed of an object launched from this planet's surface is 7.65 times 10 to the 3rd meters per second. What is the acceleration due to gravity at the surface of the planet? Right. So let's discuss what's happening here and some considerations. So we have the radius. It's saying it's equal to 3.24 times 10 to the 6th meters. V equals 7.65 10 to the 3rd. And we want to know G. All right. We know that G is defined by this, right? So G M R squared. So before the escape, we have two situations here, before the escape and after escape. So does everyone have clear that what means to escape? Escaping the gravitational interaction means that it could be neglected, right? So we are so far away that the potential that we have there is zero. Remember that we made the gravitational potential equal to zero in the infinity, right? So at the escape speed, we would say that that we don't have any gravitational interaction. That means that it's totally it's being released from that interaction, right? So before the escape, before the escape, we have the planet radius, and this thing goes with, you know, the object on the surface goes with, it's not the velocity of the planet, it's just the velocity of the object on the surface. We have some kinetic energy, right? So K1 equal to 1/2 mv squared, which is the initial velocity for the escape. And our potential energy will be minus G small m, so the mass of the, what does this say? This is an object, let's call it rocket, whatever. Big M divided by R. All right. So we have that potential energy, and it will be R because we are on the safe surface of a planet. And then after escape, after we escape that, we have the planet radius there, right? And our object is so far away, it's not experiencing any potential energy. But we also don't have any kinetic energy. That's zero. Because it's, if you take a look at what's saying here, it's talking about the escape speed. So that means the minimum velocity that you need, the minimum speed that you need to escape the gravitational interaction that the planet is applying on the rocket, right? So at that exact point where this thing is totally free from the gravitational interaction, then the speed would have been depleted. So that means that we don't have any more kinetic energy, and also we don't have any potential gravitational potential at that zone. So then we won't have any gravitational interaction there, right? So and you can imagine that you have, let's say, we have this reference for energy, and let's say you have a lot of kinetic energy at first, and a lot of, you know, negative gravitational potential energy. But at this point, let's say we are in a midpoint or something during the escape, then this kinetic energy is being depleted because this thing is the velocity is being depleted, and also the gravitational potential is becoming less negative, so it's going to zero, right? And here at this exact point where the thing has escaped, we have both at zero. All right, and this would be our total mechanical energy, right? And we can say that this energy is conserved, right? So delta E equals zero, because there is no other interaction between between the object and well, actually there's no energy being pumped into the system or drawn from the system. There are no dissipative forces, no, let's say, the atmosphere, right? The atmosphere would just slow down the object even more, not just because of gravity. Okay, so in this case, it's not saying anything about atmosphere or any viscous interaction. So we can say that the total mechanical energy is conserved, right? We have conservation of energy, and that means that delta E equals zero. So if we sum K, let's say if we do K1 plus U1 should be equal to K2 plus U2, right? And we know that this is 0 and this is 0, so this is equal to 0, okay? And K1 is 1/2 mv squared, and U1 is minus g m big M r, all right? And that's equal to 0. And it's actually, it's this case, right? Sorry, it's this that we have here. So we have a negative value here, positive value here. We sum those two, we get the line E. So those are the same in quantity, right? In joules, in modules. The quantity of joules are the same for the absolute value, right? Okay. Is that clear? Is it clear that we are applying this? If you're not applying conservation of energy, then we cannot solve this. We need to make those assumptions. And the key considerations here are these two, right? That the potential energy reaches zero, so there is no gravitational interaction at the point the object is escaping, and the kinetic energy is zero too, because the velocity, it's the minimum to escape. Of course, if we have more speed at the initial point, then it will ensure that it's escaping. But by definition, the escape speed is the minimum speed at which the object escapes the gravitational interaction. All right? Any questions about this? Okay. Cool. And so now it's pretty straightforward. We can from this we can say that big M is R V squared divided by 2G, right? And we can get G, right? So we can just substitute. We remember we had G equal to G big M R squared. So we can substitute M, and that will give us G R squared. Sorry, R squared R V squared divided by 2G. And we get rid of r, g, the square, oops, squared, and that's giving us v squared divided by 2r right there, right? And that's, if I have done the calculations right, that's giving 7.65 times 10 to the third meters per second. That's all squared, divided by 2, 3.24, 10 to the 6 meters. And that gives 9.03 meters per second squared. All right. And that's the gravitational, that's what's asking, right? It's the acceleration due to gravity, gravitation acceleration on the surface of that planet. All right. Any questions about this one? Right. Hope it's clear the energy considerations. So if you just jump from, let's say, you just jump from here and go, sorry, you just jump from here and go straight to here and just replace that arm without, you know, this, without making clear what's going on here with the energies or the situations, the first part, which is the before scape and the after scape. So we have two situations where we're comparing the energies. So if you just jump directly to that calculation of G without showing anything, then of course it won't be wrong, but you're not supporting the whole problem. So always make sure, of course, these graphs are not required, are not necessary. I'm just including them, you know, to make it clear. Sometimes the visualization of the energy as bars or like this, it's nicer to understand it. But this is fundamental, right? The consideration that there's conservation of total mechanical energy, because if not, then we won't be able to do what's next, and this relationship of M won't be valid at all, right? So those are fundamental steps, even more important than just solving the, you know, the math for this substitution. All right, so I hope that's clear. So stating the problem and stating the stages of the problem you're working with and how you're considering and what is validating your considerations, in this case, the mechanical, the conservation of the mechanical energy, that's more fundamental than just solving G, right? Or even, of course, not even replacing, even substituting with the numbers. So you've seen that we just got the numbers right here on the last step. We haven't looked at any number or any quantity before, right? And that will minimize any error or any problem that you can have when translating any miscalculation. Okay, so bear that in mind. All right, any questions about this one then? Okay, awesome. Let's move to the next one. Let's go to set 4. 7, problem 4. So problem 4 says, two satellites. Oh, okay, so it says that two satellites are in circular orbits around a planet that has a radius nine times 10⁶meters. So one satellite has mass 68 kilograms, orbital radius is 7 times 10⁶meters, and orbital speed 4,800 meters per second. The second satellite has mass 84 kilograms and orbital radius 3 times 10⁶ meter. So what is the orbital speed of this second satellite? Okay, so let me write down what's going on here. So we have the radius equal to 9 10⁶ meters. And then we have two different satellites. So let me, it's the orbital radius from the center of the planet to the center of satellite, or is it? Let me open this because I'm not seeing it. So in this case, yeah, I would say it's to the center of them, right? Yeah. All right. So you have two things here. This is for one. This would be M1 equals 68 kilograms. Actually, it's a good question, right? But for this problem, you're not even having the size of the actual satellites, right? You just have the mass and the radius of the orbit. So it will be totally neglectable. These two, you just consider them all particles, right? The radius, the orbits are much bigger than the actual the radius of the planet is much bigger than the satellites, right? So those are just particles in this case. I mean, you're not considering the interaction, the gravitational attraction of the actual satellites that are affecting the Earth or the planet. Okay, then this thing has radius 1, 7 meters, and V1 equal 4,800 meters per second. So that's for one. Then for two, we have mass is 2, that's 84. The radius of the orbit, that's 3 10⁶ meters. And we want to know V2, right? And these two have circular orbits, so if you remember the sum of forces for circular motion, we can get or acceleration in the radial direction, and that's v squared divided by the radius of that circle, right? That's circular motion. Okay. And what we can do here, the only interaction that we have between the Earth, the planet, let's say the planet and the satellites is just that gravitational interaction. So let's say we write the gravitational interaction, let's call it M for both. So we have G M, the mass of the planet, divided by R squared, and that would be equal. I mean, let me put a number here. So let's say this is 1. So from there we can get this, right? So here the interaction that we have is Fg, let's call it the gravitational interaction. And so the gravitational interaction would be equal to M V squared divided by R. Okay. Any questions from on that step? So this is just cyclical motion. Let's say we have the planet here and the satellite, and the centripetal force in this case would be the gravitational force, right? So we are getting that expression here in terms of the constant, the big G, mass of the satellite, mass of the planet divided by R squared. And in this case, R is the the distance is the radius of the orbit. All right. And from this, what you get is you get G, mass of the planet, equals R V squared. Okay, so I just canceled one this R square with the other R, and I just so we had this, right? So we had divided by R, so I just moved these R up here. Okay, so we have G, the gravitational constant, times the mass of the planet, equal the radius of the orbit, and the velocity, the speed squared, right? And we know that this right here, oops, let me get colors again. This there is constant, right? Because it's the gravitational constant multiplied by the mass of the planet, and that's not changing, right? It's not changing at all. So that is constant, and so R V squared is constant. This is constant. And so now if we write this equation for each of the satellites, 1 and 2, then we would have R1 V1 squared equals R2 V2 squared. So we have a really nice relationship between those. And remember that this is basically we're retrieving what we said in class, that this is not dependent of the masses of the satellites, right? The relationship between the radius and the velocity, right? And the speed. So the bigger the orbit, the lower your speed. Okay, and what we can do here is just solve for V2. V2, that's equal to V1, R1 divided by R2, root square, and that's for 4,800 meters per second, 7 10 to the 7th meters divided by 3 10 to the 7th, yeah, meters. And you finally get 7,330 meters per second. That's the second. The velocity, the speed of the second satellite. Right, you can see that it has less more speed than the first one, right? Because it has a smaller orbit. All right. Any questions? So you can see that the masses of a satellite, they don't affect the orbits that you're getting. Um, I mean, it's reasonable that the further satellite, which is satellite one, will move slower because you have less gravitational interaction, right? Fg is smaller, so you have less centripetal force, and so it spins faster, goes faster. Yeah. All right. Any questions about this one? Okay. Um, so now we can, I think we have time. Yeah. We can take a look at problem, let's see, problem 5. Yeah, let's continue with problem 5. Let's see. Yeah, let's take a look at problem 5, which is a non-circular one. And for the non-circular one, you just use the, remember the period. You need to have the um eccentricity and the axis. So it's quite similar, not exactly the same, but yeah, let's look at problem 5. So we can basically apply Newton's third law. Newton's Kepler's, sorry. Let me make this so red lines. Set 7, problem 5. Okay, so it says the dwarf planet Pluto has an elliptical orbit with a semi-major axis of 5.91 times 10 to the 12 and eccentricity 0.249. So you have the data for the ellipse. And it says calculate Pluto's orbital period, express your answer in seconds and in Earth years. That's it. And then Pluto's orbit around the sun. What are its closest and farthest distances from the sun? So we have a 5.91, 12 meters, centricity 1.49. So we want T period 1 D min and D max from sun. All right, and so we get Kepler's third law. So we have the period to pi a 3/2 divided by g. Yeah, let's do MS. And this goes to with the root square. And then you have d mean, that's a times 1 minus eccentricity, and d max, just a 1 plus eccentricity. Sorry. And this is basically getting the numbers there, right? So the period, we have to do t equal 2 pi 591 multiplied by 10 12 meters 3/2 divided by g, which is 6 7 10 to the minus 11 Newton meters squared kilogram squared 199 10 10 to the 30, right? Have it here. And that, let me just put this because this is getting big. So 1/2 there. And that's 7.84 by 10 to the 9 seconds. So we want it in years, right? So 1 year is 3.156 10 to the 7 seconds. And that's giving, to calculate that, 248 years. That's the period in Earth years. Okay. And for d min, oh, that's the mass of Pluto, right? Yeah, let me see if it's, let me check. Uh, the sun, sorry. Yeah, I was looking the sun for the sun. I said Pluto, but I think it's on mass. Yeah, that's why I got DS there. Yeah, so it's 1.989 times 10 to the 30. Yeah, so I put 1.99, but yeah. Thank you. Thank you, Aaron. Yes. Sorry, Varsha. I meant to say sun, but I said Pluto. Well, I was looking for the to check the number for the sun. Because you know we're calculating the orbit of Pluto around the sun. Okay, so let me get the min equal 5.91 times 10 to the 12 meters, 1 minus 0.249. That's giving you 4.44 10 to the 12 meters. That's D min. And can do the same with D max. So let's just skip those. And get that for D max. Just 738 10 to the 12 meters. You have these two here. Right. So those are the distances from the sun. Basically, this is just the direct application of Kepler's law, right? And the geometry of the orbit, right? Let's see. We have a couple of minutes, so I would like to start with some of the problems for the review, actually, and so we can gain a bit more time. These are kind of straightforward ones. So for the final, I have a couple of them, and I don't think I'll be able to cover all of them tomorrow. So maybe we can take a look at some of these, at one at least. Let's see. We can start with. We can start from the last ones to the first ones because those are the ones that we have solved less from them. So the last chapters. And let me find them. Get this back. Like, let's take a look at Flex 21, which has some, yeah, from rigid body, which has an asteroid on it, but it's not a gravitation problem. All right, let's take a look at this one. The 621. This is the rigid body problem sheet. So this one says, suppose that an asteroid traveling straight toward the center of the Earth were to collide with our planet at the equator and bury itself just below the surface. So the asteroid will be part of the Earth after the collision, right? What would have to be the mass of this asteroid in terms of the Earth mass, m, for the day to become 25% longer than it presently is as a result of the collision? So you can imagine that what's happening here is that the asteroid is changing basically changing the moment of inertia of the Earth, right? It says that assume that the asteroid is very small compared to the Earth, and that the Earth is uniform throughout. So that assumption is telling us that we are still keeping the same kind of rotation that the Earth is having, so that's not changing the way it's rotating. It's just changing um it's just changing omega, right? So you have a system that looks like this. You have the sphere, the Earth. Let's put this here. So the Earth is spinning with omega, and let's say we have this at the equator. We have big M for Earth, and we have small m for the asteroid. And we know that the initial omega of the Earth would be 2 pi divided by 24 hours, right? So that's 1 turn over 24 hours. And that's equal to 2 pi divided by 24 times 3,600 seconds. Okay, so we have that. Sorry, I got this lower than I wanted. There, right. Okay, and so the final omega that we want after the collision, that it says that it's going to be 25, the day is going to become 25% longer than it is right now. So that means that this has to be 25% slower, right? So 0.75 omega initial, right? So that's the final angular speed of the Earth after the collision needs to be 75% of the initial velocity. So we have basically 3/4 here, right? Omega I initial. And now what we can do is write the moments of inertia of the two stages. So we have the initial moment of inertia, that of a sphere, which is 2/5. Let me check it just in case, but sphere. Yeah, 2/5 m radius squared, right? And then the final, so after we got the asteroid there, we have 2/5 m r squared, the Earth, plus m r squared, right? So the mass of the satellite, which is it's saying that this is r, right? The radius. So that's the trick here, is that the asteroid is right on the. It's saying that it's colliding on the at the equator, right? So you got this r, so you can do this, right? R squared times m. So you're adding the moment of inertia of that extra mass on the surface of the Earth. Okay, so we have those two situations, and the the big physical consideration that we must apply here is that there are no external torques, right? There are no additional interactions with the system. So we can say that the variation of the angular momentum equals 0. And that means that the final equals the initial angular momentum. And that means that I final omega final equals I omega initial, initial inertia and initial speed, angular speed. And now we simply need to get the expressions for both i's and the angular velocities. So we have 2/5 r squared plus r squared. Sorry, 3/4 omega I equal to 2/5 r squared omega I. Right, just notice that we already replaced this expression for omega final. And from this, what we can do is get rid of the r's, r squares, omega I, and let's see, and then we can distribute the 3/4 and we get 3/10 m plus 3/4 small m equal 2/5 of m. And then we can solve for small m, which is 2/5 of m minus, so I'm getting the 3/10 to the other side. M, and I'm multiplying by 4/3 on this side. So that gives m equal to 4/10 minus 3/10 4/3 m. So I'm getting the m out of there, and oops, and finally you get m equal this, and that's 0.13 periodic big M. So you have the mass of the asteroid in terms of the mass of the Earth, of the planet. All right. Any questions? Okay. As you've seen, basically what we're doing here is calculate the moment of inertia before and after the collision. So it's just like adding an extra particle of mass m to your system that's rotating, and of course that will change the moment of inertia. So then we can say that this thing is basically isolated from external torques. So this the moment, the angular momentum won't change. So we can apply that right here, and as we apply that, we can say this, and we can establish this equality here. All right. Any questions about this one? This is a nice application of the conservation of angular momentum. Okay, good. So the problems for the final are gonna be similar to this, not very. You won't have to elaborate a lot. They're pretty, because there's 6 of them. So and then one question per problem. So a total of 12 things to, let's say, solve, right? And yeah, so the idea for tomorrow is to continue with these problems, and you're gonna take a look at some other with Kate in the afternoon at the discussion. And the ones that I selected are like are meant to get you refreshed some concepts for the fine. All right, and I think we can stop here for today, and we will take a look at some other problems tomorrow. Let me stop here. Let me get this thing.